forever chemicals have a menacing sounding name, and honestly, it's kind of deserved. They are toxic to many animal species, including humans, and they bioaccumulate because our bodies have just such a hard time getting rid of them. And yet, we use them. That seems absurd. Yes. But it's because the chemical properties of these poly and perfluoroalkyl substances, or PFAS, are so gosh dang useful. They make your frying pan nonstick and your mascara waterproof. And sure, I'm more than happy to switch to cast iron pans and deal with runny mascara, but we also use PFAS for applications where it's harder to do without. PFAS are used to prevent ice buildup on aircraft. They're used in medical devices. Heck, they were invented in connection with the Manhattan Project to contain uranium and plutonium. I'm not the biggest fan of forever chemicals, but I would very much like the airplane I'm flying in to be as anti-iced as possible. If we really want to get rid of these toxic chemicals, we're going to need less dangerous alternatives that have similar properties so that, as much as possible, we can substitute them in these kinds of mission-critical applications. That's what researchers in this week's story are doing. So, what are the chemical properties that make PFAS so useful for so many applications and such important ones? 1. Incredibly chemically and thermally stable. They contain carbon-fluorine bonds, the fourth strongest single bond in all of chemistry. The top 3 are also fluorine bonds. We also use PFAS because they are both water and oil repellent. That's why you got them in your nonstick coating for the oil repellent, as well as, say, your raincoat for its water repellency. At least for now. In the United States, this year saw California and New York ban the sale of clothing that contains intentionally added PFAS. Now, not all PFAS are created equal. There are a bunch of different varieties that have a different number of carbon atoms in their chemical structure. You'll see PFAS with between 1 and 8 carbon atoms in a chain. Here's one of the worst offenders in the forever chemical world. This is the molecular structure of perfluorooctanoic acid, which is a horrible name to say, but for people who actually speak chemistry, the name pretty much describes the kind of molecule you're going to get. For instance, the fluoros from all the light blue fluorine, and the octan is because there are 8 dark blue carbon atoms there, making it a long-chain PFAS. Scientists first noticed the health effects of PFAS with these long-chain versions, and that one, and its closely related counterpart, perfluorooctanosulfonic acid, were the first ones to be phased out of use throughout much of the world. Now, most of the PFAS you'll encounter are short chains with 4 to 6 carbons, or even ultra-short chains with 2 to 3 carbons. As a very broad generalization, short-chain PFAS are less toxic than long-chain, but they're also not always quite as liquid repellent. PFAS just less, both for good and ill. Now, I love that they are not absolutely maximally toxic like the long-chain ones, but they're not great. Like, these are the kind of PFAS we're still trying to get out of our raincoats. Once you get down to a single carbon atom, a single trifluoromethyl group, 1 carbon, 3 fluorine, we're actually working with a chemical our bodies can handle. Unlike short and long-chain PFAS, we can break these down and excrete them reasonably well, and they also seem okay-ish for aquatic life, which is important because that's ultimately where a bunch of these chemicals end up. In fact, there are even dozens, if not hundreds, of pharmaceuticals that contain at least one single trifluoromethyl group, from anti-tuberculosis drugs to blood pressure medication. So these single trifluoromethyl group chemicals are way safer than long or short-chain PFAS. They're not fantastic at repelling liquids on their own. Meanwhile, fluorine-free coatings have also been good, fantastic. One of the candidates is a silicone polymer, polydimethylsiloxane, which I will call PDMS from here on out because, 1, everybody else does, and 2, yeah, you only get 1 polydimethylsiloxane for free. Well, I guess 2 now. Anyway, PDMS is what gives Silly Putty its signature putty feel. It's one of the silicones sometimes used in hair conditioner. It's even used in biomedical applications to deliver drugs and in implant devices. It's biocompatible, which is to say our immune systems don't pop off at the sight of it. But it's not biodegradable, although clay minerals catalyze its degradation, so it's not a forever kind of chemical either. And that non-biodegradable, but biocompatible, is a particular sweet spot for things like implantable medical devices where you do not want to be able to biodegrade the coating and then expose your body to whatever's under that coating. PDMS has been a frontrunner in the PFAS replacement race for years. It's just, its methyl groups, CH3, aren't quite as liquid repellent as CF3, our single carbon trifluoromethyl group. But hear me out. What if we put these little fluorinated side groups onto our silicon polymer PDMS? That's exactly what these researchers did. Heating the PDMS with oxygen plasma, then replacing some of the resulting parts with the trifluoromethyl. They described it as fletching, like an arrow, at least at the molecular level. But what's important is that this fluorocarbon-etched PDMS achieved PFAS-like liquid repellency with 8 to 40 times less fluorine than a comparable short-chain PFAS. And where PDMS alone is much better at repelling water compared to oil, the fluorocarbon-etched PDMS can do it all, just like short-chain PFAS. Now, this study was just a proof of concept. Can we synthesize this fluorocarbon-etched PDMS, and is it actually any good at repelling liquid? This is the proof of concept study, and we'll need more research to make sure this coating is practical to, say, put on one of those jackets that California won't let you put PFAS on anymore. In some way or another, I end up talking about these forever chemicals, these poly and perfluoroalkyl substances, at least once a year. It's not because I'm super into organofluorine chemistry or anything. I mean, don't get me wrong. If you are into organofluorine chemistry, I get it. It's just that's not it for me. It's because forever chemicals are kind of scary. They're everywhere, they stick around forever, and they're toxic to living organisms, and that can be overwhelming. But every time we talk about forever chemicals, it's because in some new way, someone's doing something about it. Maybe it's developing a new method of actually breaking the dang things down with some common lab chemicals, or discovering there are bacteria that can metabolize them. And here, instead of breaking down the PFAS, we are now improving the supply side, finding safer alternatives to the toxic short-chain PFAS, because we're never going to stop adding to the global PFAS burden if we don't find something decent to replace it with. Each corner of PFAS research has its own take on how to chip away at the problem. And now these forever chemicals are just a little less forever, and maybe we can also still have non-stick pans that actually work. I know. I should really switch to cast iron, though. I hear it isn't even that hard to do.